CFHT, and I'm working on the observatory building and facility design for MSE. I'm humbled to be here today. I'd like to thank SPIE, the conference, and the organizers for the opportunity to talk to you today, and thank those of you in the audience for attending and your interest in CFHT and MSE. So we're excited at CFHT about this project. It's a project to basically upgrade the observatory and replace the 3.6 meter telescope with an 11.25 meter aperture telescope to do a dedicated multi-object spectrograph at different spectral resolutions. But before we get into the specifics, let's discuss why. Well, of course, science. Not only science, but better science. MSE will enable us to do transformable science and look at a diverse number of targets. It'll also be one of the critical telescopes emerging in the next bunch of large optical and infrared telescopes in the coming future. It's also going to be an essential follow-up facility for next generation imaging surveys. Here's a little bit of some of the science capabilities of MSE to give scientists in the room an example of what the capability of MSE is. If there's any more interest on that, I ask you to take a look at a colleague's papers, Alan McConaughey and Nicholas Flagey, who are working on the science aspects of MSE. So there's a white paper written by David Crampton, who said that the site for CFHT is basically priceless. And that's probably because we're one of the best sites in the Northern Hemisphere. He also said that there's inherent value in CFHT and the infrastructure we have, and that's probably because we have an established observatory that's easy to redevelop instead of building a new one from the ground up. We also can reuse the headquarters facility as a support building for this new facility. And we might as well utilize this value of the observatory and the headquarters for redevelopment plans. So the plan basically is to take CFHT and reuse the building and pier and replace the telescope and dome and get a transformation that looks something like this. Pretty similar on the bottom. So how did we get here? Well, lots of engineering and feasibility studies. We looked at the telescope pier to see what mass it could support for a new telescope. We also looked at the outer building to see what enclosure it could support. This resulted in a lot of finite element analysis of the inner telescope pier, the concrete pier, to see, as I said, what kind of mass it can support in new telescope geometry. And also the outer building was looked at to see what type of new geometry and mass enclosure it could support. And those feasibility studies were led by a colleague of mine, Kizito, if you want any more information on the engineering analysis. So to kind of go over the deconstruction plan, it's going to be pretty involved. We'll take and replace the telescope, get rid of the old 3.6 meter CFHT telescope. And since we have a larger aperture now, primary mirror, we're going to need a bigger slit opening. So we will replace the CFHT dome. And we also will need to get rid of the entire 5th floor of the observatory to increase the vertical space. And it'll end up looking something like this. You can see the entire 5th floor is gone now, and the observing level is even with the top of the telescope pier. So some of the analysis, the inner pier, as I said, didn't need any structural changes, which is great, and the outer ring foundation also did not need any changes. This is the outer ring foundation that supports the outer building, and this is the telescope inner pier. Unfortunately, there are some upgrades needed to the outer building structure, and I'll go into those next. So this is a cutaway section view of the horizontal, vertical, and radial bracing that makes up the outer building structure, and also the azimuth ring girder at the top there. And we're going to need a new azimuth ring girder for this new enclosure, and we'll also need to install some radial bracing that provides a continuous load path to the old structure from the new ring girder. Here's another cutaway section view showing the first, second, and third levels of the outer bays that alternate and are arrayed around the building. we're going to need to replace those members and upgrade them to buckling restraint braces. Luckily for us, we can do this from inside the building. Everything's bolted together with hardware, so we'll remove them from the inside and we'll put in these buckling restraint bracings. This bracing is to dampen the loads and work in the elastic zone, so it provides, it meets the requirements for the new building and seismic requirements. It'll look something like this when it's finished. We have an opportunity here to really optimize and increase the efficiency at CFHT. This is a design of the building layout for the basement, and there's a lot of details here which I won't go into, but for instance, one example is we're going to be moving the main electrical distribution panel from the second floor to the basement, where it actually comes in the building, and it just makes a lot more sense. And this is where the heat should be anyways that's being generated throughout the building. Zooming in here on the center shows the coating facility for MSE, and it's going to be in the same location as the previous coating facility for CFHT. This is where we do the stripping, the cleaning, the coating, the servicing of all the segments. We'll have a storage area, spare segment area, handling carts, optic washing stations, coating equipment, etc. And we have a dedicated elevator that we will use that goes from the observing level to the coating facility for the segments, so to safeguard and keep them safe during transport. Currently, the baseline for the coating is going to be protected silver. Here's another design of the first level. As I said, we have this really great opportunity to change things, and now we're going to have a common area that's on the first level, and this will accommodate staff and visitors when they first come in the building. And we will increase the capacity of the machine shop, and the layout's much better now to support maintenance and repairs for the summit crew. So we're developing a thermal design strategy for MSE, and I want to talk a little bit about that. It's in the preliminary stages, but primarily we're going to be removing the large heat loads in the basement and trying to minimize any kind of heat that's generated and keep it down in the basement. We're going to be using the existing building exhaust tunnels to reject the heat. And there's future work planned to calculate how much heat load we can actually remove with these current tunnels. These images show thermal images from above, and you can see the plumes coming out of the current exhaust tunnels at CFHT. We'll also be dealing with residual thermal loads, so any small loads will be, any small loads that are above the first level will be removed using heat exchangers, chilled glycol, and insulated enclosures. This is an opportunity for us to improve our heat mitigation. We want to diminish heat that's leaked into the observing level, and we have this space that's created by moving the observing level down with the top of the pier, and it creates this void, and we're going to use this as a thermal isolation barrier for the heat that's percolating up. And we'll install some vents on the outer diameter of the building and use free air to flush this space. And this is the current baseline, is doing passive flushing, but if this doesn't work out, we could always add active cooling and fans. So for the observing level mitigation, we're going to be looking at trying to address all the large surfaces, the telescope, the enclosure skin, and eliminate radiative cooling. We'll install insulation or put some shiny-like surface treatments on these. And we'll keep with doing active cooling inside the enclosure, so running air-conditioned ahus during the day, and at night we'll use vents to do passive cooling to do an air exchange and flush. So there's a future plan also to look at the steady-state simple thermal analysis of these surfaces. And I'm currently working on a document that outlines the functional requirements for the observatory building and facility. I want to share with you a few examples of some of these requirements. Limit heat parasitically leaking through the observing floor. We talked about that earlier, and also minimize heat that makes it into the optical beam. Wanted to give you a basic overview of the MSE Observatory. It's a prime focus telescope with a 60 segment M1. We talked about the telescope outer building and inner pier. We'll have a low moderate resolution spectrograph on spectrograph platforms on the telescope, And the high-resolution spectrographs will be located in the inner pier on the 3rd floor level. We have a wide field corrector and ADC at prime focus. It's a dome. The dome is a cloth-style enclosure with vents. And we have a fiber positioning system at the top with over 1,000 fibers for high resolution and maybe 4,000 fibers on medium low. As I said, Kizito worked on he has a paper that he's worked on the system overview, so take a look at his paper and his talk. So here's the current CFHT building on Mauna Kea, and I'd like to share with you the vision of CFHT for a future MSE Observatory. My closing remarks, as you can see, it's little difference on the outside, but it's very transformative on the inside. The knowledge and experience of CFHT and the astronomy community will create a modern, optimized, and scientific, great data collecting machine. And will provide kind of a missing spot and a capability for the astronomy community. I'd like to thank all my colleagues that work with me on this project, and thank everybody for their time today, and take any kind of questions you might have. Thanks very much.
We have time for a few questions.
Can you talk a little bit about some of the other limitations of infrastructure on this upgrade, for example, electrical power, other types of utilities? You mentioned the structure.
Structurally wise, these are the only things that we found that to be limiting or need to be upgraded. Electrical, I mentioned, we're going to basically redesign the whole electrical system, so we'll move the main distribution room down to the basement. We're going to try to reuse electrical wherever we can, same with plumbing for domestic water, and there's really, I think the biggest thing is the 5th floor. You know, we're removing all of that structure, all of the concrete, and putting in a new structure. So that's going to be quite an undertaking. Jose?
Morning, Steve. What code did you?
This mic there, or you can speak louder.
What code did you use when you interpreted the structural design on this?
DSL did those feasibility studies, so it's in the paper that we have.
Thank you.
It's the newer building code. I think it's 2007.
Yep.
What schedule do you consider to be put in operation?
That's a great question. I invite you to go to a talk that a colleague of mine, Rick Marinsky, is going to give, and it talks about the project schedule for MSE.
You know when is the talk?
Rick?
Wednesday afternoon.
Wednesday afternoon.
In here.
In here.
Sorry for the suspense.
What about the site? Can you do these changes?
Well, you know, this is an upgrade project, and we've sort of designed it that way so we don't disturb the site. It's very important to us to keep environmentally the site the same way it is. A lot of these changes will be done on the inside of the building, and then of course, you know, we'll have to do construction where we take apart the dome, take apart the telescope, but we're trying not to disturb the site as much as possible. But it is feasible, and you know, if the partners come together and everything works out, it'll go forward. That's a tough question to answer. It's kind of a loaded question.
That's why you asked.
Is 11.2 meters the largest size of the primary mirror?
I believe so. You know, Derek Salmon actually looked at some different sizes of what aperture we could fit in. It seemed like 11.25 meters is sort of the sweet spot for getting vertical clearance still and having a taller telescope still fit and not making the enclosure much bigger. So that's what we came up with. Thanks.
Thank you. Let's thank the speaker again.